All right, welcome back to System Software. So today is the last lecture of the main content of the course. We're going to be finishing up the compiler implementation and finishing up how we can implement pointers, how we compile code that uses pointers. So last time, if you remember, we went over pointer operations in simple IR. They're really just the same as C, where we have reference, dereference, and assignment to a dereferenced variable. Questions on the semantics of simple IR, questions on the meaning of these. I think everyone has seen this in C already. It has the same semantics. But any questions on the meaning of these operations, the IR operations? Yeah. 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 In this stack frame, you're saying RBP doesn't have a value? So is RBP in memory or is RBP a register? It's a register, yeah. So how is the RBP register assigned and maintained? Who sets RBP? What's that? Well, the compiler generates code, and what code does it generate to set RBP? When does RBP get assigned in the code you generate? Yeah.
When the caller calls a function?
Yeah, in the function prologue. Well, it's not the caller, it's the callee that does it. And it's the prologue code. The prologue code assigns RBP. So this prologue code, this is where RBP actually gets assigned. So remember, RBP, as long as you've implemented the calling convention correctly, RBP will always hold a pointer to the stack frame. So you can think of this as an invariant. At any point in the program, RBP holds a pointer to the stack frame. And because the compiler ensures that invariant, that condition always holds, whenever you generate code, you can always rely on RBP holding a pointer to the stack frame. That's how all of this pointer stuff will work. Yeah?
This is just a general question, but does simple IR support strings and chars and floats?
Not explicitly in the language. But remember, strings and characters, those are just, so strings are just arrays of characters, and characters are just numbers.
Yeah.
So, I mean, characters are like
1 byte?
8-bit, 1 byte numbers. So you'd have to do some cleverness you'd have to decide on whether you want to put 8 bits in every 64-bit integer and make an array that way. But I actually have an example. I didn't go too much into the examples. So I gave you some examples. These are more for like complete compilers. These are more for me when I was writing the compiler to help like work out the whole thing. And I ended up giving you sort of more micro tests for each piece of the compiler. But we can actually call malloc from IR like this, and you get a pointer. What does malloc return? Malloc returns a pointer. So now x is a pointer, and I can play with that pointer. I can add to it. I can subtract from it just like any other number. I mean, you can call the realloc function if you want. Is a realloc a function or is it a macro? It's probably a function, yeah. Whatever C function you want to call, because we follow the System 5 application binary interface, we can call functions and get their return values.
And I assume you can free it them too, right?
Yeah, you could call free, passing the parameter. Now there are issues with data types. You'll have problems passing parameters of the right data type. So it won't work perfectly with C because of data type widths. But you could, in assembly, for instance, in assembly, can you work with strings and characters? Yes, right? There's no types, but you can work with them because it's just binary data. And as long as you can access sort of arbitrary memory using pointers, then you can do mostly what you can do in C. Okay. All right, other questions on anything from last time? So yeah.
Can we do the homework question real quick?
Okay, sure. Let's see, what did I ask? If the variable x has an offset of negative 24 from the base pointer, write x86-64 assembly code that will result in the address of x being stored in register RAX. Okay, so let's look to this example, actually have that. So here is, I think it was just taken from the example we had yesterday. So here is a stack frame for a call to some function, doesn't really matter what the function is. And you can see that x has offset negative 24 from RBP. Questions on this setup? So we saw this like pretty much every lecture for the past like several weeks. This is the stack frame. RBP holds the address pointing to the stack frame, that is pointing to this entry. And with our compiler, we map each local variable to an entry in the stack frame. And because we don't know where the stack frame will be, the actual address of the stack frame at runtime, or we don't have to know, it's going to be an RBP, we access variables using what? How do we access variables from RBP?
Offset.
Yeah, we use this offset from RBP, and there's this syntax in the Intel world for doing exactly that. So what does, in the context of this function, which defines these local variables, what does this assembly operation do? Yeah.
It accesses 8 and moves that into RX.
Right, accesses 8. Why does it access 8?
Because it dereferences the value at 24 from the baseline.
Yeah, exactly. So this is saying take whatever the value of RBP is, which is 80, and that value, because of the calling convention, holds a pointer to the stack frame, and then subtract 24 from it, so you get 56, and get whatever value at memory there is. Load that value from memory. So this is like an indirect load, or a load from memory, where you specify the memory address in a register instead of hard coding the actual address. And it stores that value into the RAX register. Questions on that? Yeah.
In dips, we had a save word and a load word.
Instruction up.
And we don't really, I don't really know what that would be most similar to.
I don't know MIPS, so I guess would it take a register?
Yeah.
And that register would hold the address, or no?
Okay.
I don't know. I don't know MIPS. I just know the Intel world. But I'm sure you can do the same thing, probably with several instructions in the MIPS world. Yeah.
But didn't the homework ask us for the address of X?
Ah, yes. So this isn't answering the homework. This is just making sure you understand this. So the homework question was, if the variable x is offset negative 24, so this is how you would access the value of x, how do we get the address of x and store that in RAX? So this doesn't do that. This stores 8 in RAX. But what we really want to do is get, what's the address of x? 56. 56 stored in x. Yeah.
So to get the address of x, actually you would first save the value of the RBP into RAX.
Okay.
The offset from RBP, which is x dot, to RAX, including RAX. Then after that, you would load the value of RAX into the address of T.
Did I have T1? So I just stopped it just to put it in RAX. So you're moving on to the full instruction, which is good. So just to reiterate what your classmate said, sorry, not RBX. We take, so instead of asking Intel or the processor to load from memory the address given by RBP minus 24, we want what that address is. So internally, the processor is computing that. But this instruction is just going to do a load from that address. We want the actual address itself. And that's not stored anywhere explicitly, but we can compute it in the same way that we know that we can use an offset from RBP to access the value of x. We can use that same information to compute the address of x. So to do that, we take RBP and move it into some register. And then we add the offset from RBP for x to RAX. And that's it. You're done. You've solved the homework. So what's that? Yeah, that's how you compute the address of a variable in assembly or generate code to do it. in assembly for any stack frame layout, or for any stack frame position in memory. Yeah?
Does it dereference RBP in that first line and store it for RAX? What is stored inside RAX?
Okay, so we have a question. So what happens if we, instead of, so like this, right, dereferenced RBP. In this example, what would RAX hold at this point? 8. Okay, so we have a couple of questions. We have 80. We have old RBP. Who says RBP, or the value of RBP? Who says old RBP? Good, it's old RBP. So remember, in this example, when we did move RBP to RAX, this copied the value that RBP. So remember, RBP is a register, not memory. So registers, they're just named and they hold 64-bit data. So the value of RBP is 80. So when you copy the value of RBP into RAX, RAX is now 80. If you do an indirect copy, that is, you load whatever the address of that RBP holds, you load that value in memory, you're going to get whatever the old RBP is into RAX. Does that answer your question? Questions on that? The difference? So these parentheses in assembly really is like dereference of a register. So you either have the register value itself or the value of memory that the register points to. So this is what makes RBP a pointer, the fact that you look up you do a load from the address that register holds. So remember, whether it's an address or an integer or a character, the machine has no built-in representation that records whether something has a specific data type. That's all kind of an artifice created by the programming language. Instead, it's whatever instruction you give to the machine. That instruction will interpret the value as being an address or an integer. There's no characters or strings at the machine level either. Characters are also just numbers. Yeah?
Out of security and curiosity, if you did parentheses -24 RBP and put before those parentheses, all parentheses, an offset from X, would that give you the value that's at?
Do you mean you kind of do like a double parentheses? Wait, say again? Describe again?
So
Like this? Like two sets of parentheses?
yeah, and put a number before that for both parentheses. Would that give you like another?
Like doing this?
Yeah, or that.
I don't think so. I don't think the processor supports that. You'd have to first, that would be like a double pointer, right? You'd have to just do each pointer operation separately. So you have to put that in RAX and then do another like offset from whatever RAX is. I don't think you can do both of those. But yeah, good question. This would be like basically saying RAX is an array, or if X is at -24 and your language has some operation to access index 18 or index -18 from that variable, that's how array indices work. Remember, arrays are really just pointers, and when like in C, if you were to say, give me the -18th, well, it's a little different because this is, well, okay. So let me give an example that's separate from the assembly one. But when you say X, give me the second index of X. So first of all, which element is this? Yeah. It's the third element. So what's really going on, and what you could actually just basically translate this to, is X plus 2 dereference. It's the same thing. And translating this to our offset level, this is where data types come in. This is really like the offset in bytes is however wide X is. So if it's an integer on a 64-bit machine, this X offset is 64. Okay, now I'm confusing myself. 64 bits, right, or 2 bytes. No, what am I saying here? So each character is 4 bytes, so this would be 4 times 2, 8 bytes. So you would do 8 offset from RAX, assuming RAX holds the value of X, which was the pointer. Anyway, what's that?
So like Z, whenever you're doing like X plus 2, it automatically multiplies.
Yeah, I think even the pointer arithmetic does that as well. It multiplies it by the bit width or the byte width of the data type. So that's where it does differ a little from assembly, where assembly you're dealing with byte addressing, and in C they're using the data type, the width of the data type. But anyway, don't worry about this too much. You don't have to worry about this. If you want to, like, as a bonus project, implement, say, an array index in simple IR, you could do that, or implement a compiler from another language to simple IR that uses array indices. You could do that as well. But this is a good transformation to keep in mind about what's really happening with arrays. They're really just a syntactic sugar for pointer manipulation.
Do like if you have a single pointer with one thing in it, right? Couldn't you just do an array syntax address at 0 with an offset of 0?
I think you probably could. The type checker may complain. Actually, yeah, I think you can do that. It depends on what the C type checker does. I can't remember if it might warn you and say, hey, you didn't declare this as an array. But technically, yeah, you could totally do that. You could take any pointer and access it using array syntax. Modern compilers may complain to you, especially if their strict checking turn on. But yeah, you can do that. The converse is true, or the inverse is true here. All right, so any other questions on homework 21? This is the answer to homework 21, just to be clear. I know we went on a lot of tangents, but this is the answer to homework 21. You just generate assembly code that does the computation of the address from RBP and the offset. Yeah.
That's the last homework.
That's the last homework. So I asked the grader to just give everyone credit for 22, 23, and 24, because I really wanted the homeworks to be 1 point each. But you all just get free credit for 22, 23, and 24, because we lost those days. Okay, and that was the first step in implementing the reference instruction. So to get the reference, in order to get a reference to X, we need to figure out what its address is. To figure out its address, we generate code that computes RBP plus whatever its offset is. And then, as your fellow classmate pointed out, the rest of the instruction semantics is to save that address into whatever the left-hand side variable is, T1 in this case. And so that just works like any other assignment where we store the value into the address associated with T1. Questions on that? And then dereferencing, use this. So this is what I think someone else was asking about. This parentheses syntax without an offset will just be effectively offset of 0, as somebody pointed out. And this will load the memory at the address given by RAX. So this assembly instruction is how we're going to implement dereference. So T2 equals the dereference of T1. So without any data types, there's nothing enforcing that T1 is a valid address. But just like in assembly, this is going to assume that T1 is an address and try to dereference it, try to load the value at that address. And just as a refresher, I think I did this at the very end, so let me go over this again. So this is the same stack frame that we have before. We're doing T2 equals star T1. So we're trying to assign T2 to not the value of T1, but the value that T1 points to. It happens to point to X, but there's nothing explicit that says that. It just has an address in this field. So the assembly to do that is to first, and let me write down again what these steps look like. So the first instruction is to move negative, actually let me do it this way, since my writing is very bad. So this is trying to compile this instruction. So T1 is here, T2 is here. When we do move negative 40 RBP, so what variable corresponds to negative 40 RBP?
T1.
This is T1. And we move the address or the value?
The value.
The value. This is 56. So this is, after this happens, RAX holds the value 56. Questions on that? This is the regular store or load of a variable that we've used before for like enter assign. And this instruction, this doesn't take the value of RAX, but it uses RAX as an address and does a load from memory.
So that's the D reference.
That's what?
That's the D reference.
That's the D reference. That's the D reference. So it takes whatever value RAX has, in this case 56, and it uses that address to do a load from memory at address 56. So what's at address 56?
8.
The value 8. So after you run this instruction, RBX holds 8. So we store whatever value is at the address given by RAX into RBX. That address is just whatever the value of T1 was, because that's what a pointer is. A pointer is just a regular variable that happens to hold an address or happens to hold a number that will be interpreted as an address. All right, and then finally, we take whatever RBX is and we store it here. So what variable does this correspond to?
T2.
Yeah, T2. So this is T2. T2 has negative 48 offset. And then after I run this store, this move, how will the state of registers and or memory change or not change?
It won't change.
What won't change? Or what will change? Let's start with what will change. What will change in this whole picture?
T2 gets assigned to 8, points to 8. No, T2 becomes 8. So T2
So effectively T2, but what is, so yeah, so we said that this is T2. So what, okay, T2 becomes 8, but how does the memory or registers change? So yeah, we know semantically T2 is supposed to become 8, but there's no notion of T2 at the machine level. Yeah.
Pretty much, I'm pretty confused, but I think wouldn't just when the value of x be loaded into where the address memory of T2?
Yeah. So maybe I'm splitting hairs a little bit. But my point is that it's not T2 that gets changed. It's this entry, this address 32 that gets changed. Now, in the compiler, we correlate or we make a mapping from T2 to that address. And I know I'm splitting hairs a little bit. But the state of this machine changing is not T2 because there's nothing in the machine that corresponds to T2 at the assembly level. It's this space in memory that now changes. So this instruction takes whatever's in RBX, which is 8 right now, and it loads it into this memory address given by RBP minus 48, which is 32. So RBP is 80 minus 48 is 32. So this is the address that gets loaded, and this now becomes 8. So sorry for splitting hairs a little bit, but I just wanted to make it clear that at the assembly level, the only things you can change are registers and memory, besides I/O. But for the code that we generate, we're just going to be changing the state of memory and registers. So now, so the address, and so just to violate my own splitting hairs, T2 will now equal 8, but it's really the address 32. Like, I don't know how to say this. 32 in memory now equals 8. Questions on this? Yeah.
So at least for the sake of this class, it only ever stores addresses or values. We don't store anything else instead.
Yeah, basically, yeah. I mean, addresses are values, but yeah, in terms of the semantics of the language, we only have 64-bit integers and addresses. Those are the only data types that we're dealing with. But remember, everything in the machine is just integers or binary data, and all kinds of data can be represented with those bits. So the notion of types in the programming language is not like physically embodied in the machine. It's like in a kind of strict sense. But you can always encode data. Just like when you download a picture or listen to music, that's all being encoded as binary data. And your programming language probably doesn't know about, say, bitmap images or music data, but you can still process it with an algorithm to interpret it as that kind of data. All right, questions on this? So it's just like an assign between T1 and T2, except we take the value of T1 and first do an indirect lookup. We do a load from that address that T1 has, and then store it into the left-hand side T2. Yeah?
What will happen if you try to do an instruction with parentheses RBX that is out of the stack for that function?
Out of the stack, so you'll just do a lookup into some memory location, some other memory location. So it's the same question as like what happens if I do an out of bounds access of an array. If that memory space is accessible, you'll just get that value. You'll get the value of that memory location. So for instance, maybe it was address 100, or you could write in simple IR if you wanted. You could say T1 equals 100, and then you could just dereference it if you like. Just like in C, you can do the same thing. And you'll just get 100 will probably give you a segfault because I don't think the OS or the kernel will allow your process to access memory there, or if you're trying to write it. You won't be able to read it. Actually, even maybe not. But it'll just literally do what you ask. It'll dereference that memory address and get whatever value is there. There are protections in the hardware level to prevent you from accessing certain memory addresses. But without that, you'll just access that memory. So this is exactly what happens when you have like a buffer overflow in C, or when you access an array out of bounds. Most compilers are not going to stop you because it's very hard to check that at compile time. And then most compilers, so the C language technically calls this undefined behavior, which means the compiler is free to do whatever it wants. And it usually does the easiest thing for the compiler. And it's really supposed to be on you, the developer, to not do that. But what will end up happening for most compilers is it'll just access data out of the bounds of that array, and it may end up being data from another array. It may be unallocated data. And then your program won't behave as you expect because you weren't supposed to do that. It'll change. It might change behavior every time you run it, or it may give you unexpected behavior. Yeah?
Okay, so I got really confused on like the first two lines, right? Or I guess the second line.
These two lines? The second line.
If you're dereferencing RAX, how is that different from just normally, or like not dereferencing it, but without the parentheses? Because isn't it on those bounds? This is kind of a look.
So let's do the version where you don't dereference it. Let's see what happens when you don't dereference it. So the first step is the same, RAX equals 56. And with the dereference, RBX equal to 8. What would RBX equal instead when you move RAX to RBX? RAX is 56. What will RBX be now? 56, right? So if RAX is 56 and you move RAX to RBX, RBX is now 56. So that's here. That's like this address, but we're not dereferencing it. And then how will this change? RBX is 56, so now what will the memory address associated with T2? Yeah, it'll be 56. So this will be assigned to 56. Does that make sense? So we're just copying the value of T1 instead of going to the memory address that it points to. Okay. So that's a review from last time, and I know actually at the end of class, I guess I sort of quickly went through the rest of that dereferencing a pointer. So now let's look at assigning to a pointer. Let me get the... Oops. So let's look at pointer assignment. So in this case, we're not loading from a pointer, we're storing to a pointer. We're storing to the dereferenced address of a pointer. So the semantics of this is T1 is expected to be an address, or was treated as an address, and we take whatever the value of the right-hand side is, and we store it at the address given by T1. We don't store it in the stack frame location associated with T1, but we take whatever the value of T1 is and go to that address and store the right-hand side. Questions on this? Okay, so this is our same program. Just to refresh you, we have x equals 8, y equals 9. We get the address of x stored in T1. So remember, T1 now holds the address of x, not the value of x, the address of x. In our machine here, T1 holds 56 because that's the address of x. And then we assign the dereference of T1, which is 8, and we assign that to T2. And then the next instruction is to assign to the pointer, the address that T1 points to, assign 11 to it. So how will this picture change after the instruction star T1 equals 11? Yeah.
I just have a quick question.
Yeah.
How do you know the RVP is
80? What sets the RVP? What sets RVP?
the old address?
No, who sets RVP?
The callee.
Oh,
The callee, yeah. The callee it sets it every time. So this is an example of what RVP might be at runtime. The code we generate is independent of what value RVP is, the actual value of RVP. But this is a snapshot of a single call to the function.
made it up.
I made up 80 for this particular call to have a concrete number.
And then you know each variable has 8 bits or bytes of offset rates.
Right. So after we do star T1, do an assignment to the dereference of T1, assign it to 11, how will this picture change? How will the stack frame change? Yeah.
11 is now stored at the memory address associated with T1, so it's going to be, well, it'll be stored at the negative 40 offset of RBP. Is that correct?
So you're saying the negative 40 offset of, so why negative 40?
Because that's the memory address associated with T1.
So you're saying this will change to 11. What if I have, say, okay, good, yeah. So if I said T1 equals 11, then this slot would change to 11. Star T1, right, so it takes the address that's at T1 and stores whatever value we gave it at that address. So T1 holds address 56. So when we do a dereference assignment, it's going to store not overwriting T1's address, but overwriting whatever address that T1 has. T1's address is 56, which is here. So that's going to update this value. That's going to update this value to 11. Questions on this? Questions on this behavior? And then I guess just to finish it out, when we say T3 equals X, what's the value? How's this going to change? Yeah.
So now the 11 will be stored with the memory address of T3.
Say again.
I said 11 will be stored with the memory address associated with
Right, exactly. So 11 will be stored at the memory address associated with T3. So this is how normal assignment works, non-pointer assignment works. And notice that we never reassigned X here. This is what pointers, the consequence of pointers. We never reassigned X explicitly, but because we had a pointer to its address, we could reassign X's actual value, the value at the memory address associated with X, we could reassign it through that pointer, which is why assigning X to T3 now makes T3 11 and not 8, as it might look by looking kind of sort of naively at the code. Questions on this? Yeah.
How does it tell the difference if it's a value stored or an address? So if it sees 11, how does it know that that's not an address pointing to 11?
It doesn't. So if we had then written another instruction like star T3, equals X, then the machine would take 11, go to that memory address, and store to it. And so without memory protections, I mean, this is because you as the programmer, like in assembly, are free to read and write from memory locations as you like. This is the process model, that you have your own address space and you can read and write data however you like. Pointers are just a kind of a data type for us to help us recognize the difference between those two. Rather than at the assembly level, you'd have to use either a straight up register copy or a load or an indirect load from a register. You can think of these data types as sort of translating into assembly operations, different assembly operations. Does that answer your question? Okay, so that's the behavior of doing this dereference assignment in simple IR. So let's see how to do this in the assembly level. Okay, so what assembly instruction can store a value to an address? So we saw when we did the dereference load how to load from an address. Yeah, how can we do it? How can we store to an address?
Move, you dereference the value you want to put into it. Just register again?
Well, yeah, we'll do that, but how would we do the store? How would we do the store? How would we do this update of T2? Or wait, which update? I'm confusing myself here. Yeah, how would we do this update? So it turns out it's the same thing that we saw when loading from a dereferenced pointer, but we just put it in the destination operand. So you can use the same syntax, the same operation syntax in assembly, but instead of loading from an indirect register address, we store to the indirect register address. Yeah, you just store to the dereferenced address instead of loading from the dereferenced address. So this is kind of the easy part of assembly, but Intel assembly, but also the kind of confusing part is that all of these move operations look really similar syntactically, but sometimes they're doing a register copy, sometimes they're doing a memory load, sometimes they're doing a memory store, sometimes they're doing some offset loads and stores for you. But if you just remember that when you put parentheses around a register, it means do a load or a store at the address given by the register. Then hopefully remember that. As long as you remember the right second operand is destination, this is doing the dereference assign. If it were on this side, it would be the dereference load.
So we're assuming basically RX is already holding an address?
Yeah, assuming it already holds the address. So knowing this instruction now, let's actually build a sequence of instructions that will implement this simple IR instruction for us. So we'll want to get the value that we want to store into RBX and get the address that we want to store to in RAX and then do the move. All right, this is, I thought I updated this, but I didn't. So let's just go through the, let's go through it. Yeah, no, let's just go through it. Okay, so just like before, we get the value of T1 and save it into an address, or save it into a register. So now RAX holds the address, or holds the value of T1. It holds the value of T1, just like any assignment. Anytime we want to get the value of a variable, this is how we do it in the Intel assembly world. So just a quick refresher, what does this -40 mean? Why is it -40?
It's the offset.
Yeah, it's the offset for T1 in our symbol table. And at runtime, that's going to be the offset from RBP that will hold the stack frame entry that we'll use for T1. Okay. And then, so the order doesn't really matter between these two instructions. And this is the way I wrote my compiler. Here, I'm storing the value, the right-hand side value, into RBX. You could certainly do an immediate load or immediate store if you wanted. You could reduce the number of operations or swap these around. This is how I wrote my compiler to do it. So now we've got RAX holding the value of T1, which is the left-hand side variable name, and we have RBX holding the value of the right-hand side, which is 11. All good on this? Questions on the state of the machine right now? RAX holds the value of T1. RBX holds 11. And now this is where we use that indirect store. We're not copying 11 to the entry of T1, to that stack frame. We're copying it to whatever the address T1 had. So this is whatever RAX its address, store the value of RBX to RAX, the address RAX. All right, let's take a look at this in our machine. So let me put the state back to where it was before we ran this instruction. Can anyone not read this? Is this too small? Too small? Okay, let me put it here and blow it up. Okay, so here's our assembly. Here's the state of our machine. All right, so negative 40 RBP, which memory address does this correspond to? T1. This, well, it's right here, negative 40 here, or 40. It's actually 40. It just so happens that because RBP is 80 and we subtract 40, it's actually memory address 40. All right, so now what's the value of RAX? Looking at this state of memory, what's the value of RAX after? Yeah.
The memory address of X should be 56, correct?
Yeah. What's that? So it is the memory address of X, but nothing in the machine knows this. We know it. But just looking at the state of the machine, because this corresponds to address 40 here, this is the offset for T1, this move instruction loads whatever the value in address 40 is and loads it into RAX. So the value here at address 40 is 56. So this 40 is 80 minus 40. That's why it's 40. So now RAX holds 56. After this instruction, what does RBX hold? 11. Yeah, it holds 11. All right, question so far here. So we've set up two temporary registers for ourselves, RAX, which holds the value of T1, and RBX, which holds the right-hand side of our instruction. So remember, we are trying to compile this instruction. So this is getting the value of T1 first, not star T1, but T1, and getting the value of 11, the right-hand side. And now this is where all the dereference magic happens. Remember, RBX is 11 here, RAX is 56. So how does the state of the machine change, either registers or memory? How does the state of the machine change when we do move RBX to parentheses RAX? Yeah, up there. Say again? So how does the state of the machine, so tell me the address of, in memory, that changes. What address in memory changes here? So these are the addresses in memory. So which of these addresses changes? 56, address 56. So we know it's X, but the literal machine instruction has RAX being 56. So there's nothing in the machine that knows that 56 is associated with X. Our compiler knows that, but the generated code doesn't. So this just takes whatever value is in RAX right now, which is 56, and stores RBX into that address. So this will overwrite the current value 8 with 11. Questions on this? All right, so that's pointer assignment. Let's do one more exercise. Let's do star T1 equals T2. So a slightly more complicated dereference assignment. So what instruction, yeah?
Just to clarify,
Yeah.
T2 is a holding value non-negative, correct?
Yeah, I mean, remember, they're all just values. So we could dereference it. There's nothing in our language stopping that. But in terms of like the semantics of our original input language, yeah, it's not meant to be an address. It's not meant to be an address. No problem. All right, so let's generate assembly code that will implement this statement, which is assigning the value of T2 into the address stored in T1. Yeah.
I think the first thing we should do is assign or move -40 over stop, which is basically T1's memory address, into RAX.
Okay, so same thing that we did before. Actually, let me show the other code because that's probably make it a little easier. So we load the value of T1 into RAX. And so what does RAX now hold? RAX holds 56. So we're loading the value of T1. Okay, so we load the value of T1 into RAX. Yeah, so some of that, yeah. What should we do? What can we do next?
Parentheses, RAX to negative 56 RBP. Move it to T2.
So we won't be able to do a load and a store at the same time. So let's do these one at a time.
Move that to RBX.
Okay. So RAX holds 56. And what will the value of RBX be after this? 11. Okay. So what's supposed to be, so right now T1, before this operation, T1 equals 56 and T2 equals 8. So what will be the value of variables after we run this? And I guess x is 11. What's that?
X remains the same, T1 remains the same, and T2 becomes 11.
So you're saying this assigns T2 11. This statement assigns T2 to 11.
No, sorry, 11 to T2.
Ah, yeah. So this is assigning this isn't assigning T2. This is assigning the address associated with T1. So what's the state of the machine after?
X will now equal 8.
X will now equal 8. That's the state after this instruction. And so this is loading the address of T1 into something. But we actually want to do the opposite. We want to store to it. So what's the next instruction?
Then we should get the value of T2.
Okay, so how do we get the value of T2?
It would be minus 32 RPD.
So the offset is 48, actually. This is the address. So this is loading T2 into, let's just use RBX. So now RBX load the value of T2 into RBX. So now what's RBX equal? 8.
And now you can take the other one.
Okay, so now we can update the other one. So how do we do that? Someone else? Yeah.
You say a move percent RBX and then a parenthesis around RX.
Move percent RB. Is it like this?
Normal RBX
Normal RBX,
and then do
like this. So we're storing RBX, which is holding the value of T2, into the address of RAX. So I'm running out of text space here. The address of RAX is star. This is like into star T1. What's that? Yeah, I think that's right. It's the same as up here. So it's the same thing as this, except the only difference is we load the right-hand side value from a variable. But the rest of the set of instructions can be the same. You get the address, or you get the value of T1, and then do an indirect store into the value of T1. All right, so let's see what the machine does after we do star T1 equals T2 and make sure it actually comports with the state changes that we wrote here. All right, so we load -40 offset into RAX, so that's 56. So indeed, RAX will be 56 at this point. And then we load offset -48 from RBP into RBX, and that indeed is 8, so RBX will now hold 8. And then we store RBX into the address 56. So the address 56 is here, and RBX is 8, so this will overwrite the memory address 56 with 8. And because that is the memory address associated with X in our compiler, in the semantics of our input language, indeed 8 will now be, X will now be equal to 8. Questions on this? So yeah, so take some time to wrap your head around these instructions. And as I said before, the tricky part here is that in some sense, these variables are pointers. They're not pointers, they're references. The compiler manages which address they're associated with in the stack frame. But what distinguishes that from a pointer is that a pointer is when you take the address and store it in one of these memory locations, when you store some value that is meant to be used as an address. And there's different syntax and different operations in assembly for allowing you to do this kind of indirect loads and stores from a value in a register, or that value is an address, from an address in a register. Yeah?
So, all you consider, if we don't dereference a register, that is just kind of using it as the value.
Exactly.
If we do parentheses and dereference it, we're using that as a pointer. Exactly. So you can really think of this as the assembly version of like star T1 in the assembly world. And in like, I get probably MIPS or other instruction sets that have, more simple, like a reduced instruction set. This may be you may have to do this multiple steps. I'm actually not sure. I don't know MIPS. But assembly eventually gives you single pointers. They also have to be registers. You can't do a dereference of, like you couldn't put parentheses around this and do a dereference of an address load. So it doesn't give you the full power that, say, C has or even simple IR has, because you have to first take these values and put them into temporary registers. But yeah, this parentheses is the assembly version of dereference. All right, questions on this? All right, so choose your own adventure. Should we go over CodeGen 4, or should I just go through the whole code example and go through all the state changes? Who wants to see all the state changes in the example? No. Who wants to see CodeGen 4? All right, let's see CodeGen 4 first, then if there's time, we'll do that as well to put it all together.
Is that what the putting it all together lecture was supposed to be?
That was really like a placeholder because I wasn't sure what to do. I wasn't sure about timing, how that would work. I think it was going to be putting the whole compiler together, actually, is what I intended. All right, let's look at CodeGen 4 first. So the instructions are really similar to CodeGen 3 because I just copied them from CodeGen 3. But I've given you another template. The template is really similar to CodeGen 3, where I've given you local vars and assignment already. And then these are the only 3 functions you need to implement. And in terms of code size, this project is actually really short. But because of all this and all this, it's a little harder to wrap your head around because you have to really be careful with, am I doing loading the value of a variable, or am I like dereferencing that value as an address? So it'll be a little tricky to get it right, I think. But actually the code is deceptively small. It's very short code. There's not a lot of conditional code you have to do. You just generate these templates and fill in the pieces. Yeah?
Time-wise, I'd probably about like 15 minutes max, if you understand the concept pretty well.
I mean, yeah, if you totally get all of these, probably. If you get these snippets of code, like these, there's really only 3 templates. Yeah, if you grasp all those, and you're already familiar with Python and plugging in the variables, it could be very quick. I don't want to say it'll be quick for everyone, but yes, I think you could do it in 15 minutes if you grasp all this, for sure. It could be very fast. But remember, you got to test it, make sure it works, test different variations of it. But yes, you could do this quite quickly after you wrap your head around what these are supposed to do. Questions on the template? It's just like CodeGen 3. And just like CodeGen 3, I've designed the grading so that you don't have to have the full compiler. And when you submit it, you should just only submit these 3 with a template. I think I said this last time, but if you want another bonus project, make a full compiler for the bonus project, put all the pieces together into a single codegen.py, and then you'll see the magic of having a full compiler and the thrill of seeing the whole compiler. Yeah, you can do that as a bonus project too. But you got to like get all of them right and show some of the. I've given you a bunch of more sophisticated examples, like this malloc example. So one cool part is you'll actually be able to use like malloc and play with pointers if you get all of this stuff working right. So this is function calls, this is arithmetic operations, this is pointer operations. If you get those all working, you'll be able to do some fairly full-featured programs. Yeah.
What's the size for that 8 times 4?
Because I think I don't know, I did like 4 bytes. I don't know. Or maybe I did 4 entries and then 8 bytes. As you can see, without data types or any specification, the meaning of this, the meaning of these data types gets lost because it's all just binary data. I think I intended this as like a 4-entry array or something. And then you could like do some pointer arithmetic to actually access the other elements of that array. So yeah, use that as a potential bonus project, putting all these pieces together and showing me that these examples work. But anyway, for CodeGen 4, yeah, these are all you have to do. And just like with operations, you can really just print out an assembly template. So this is not a template, but you can kind of reverse engineer the template from this. You just need to plug in the variable, the right-hand side variable, or the immediate value, and do this, and then you're basically done for assignment. And it's the same for reference and dereference. Let's see what else is in here. So I gave some descriptions of, I gave you the examples of all of these, just like we had in class. So this is not a template, but this is an example. You can create a template from it. This is an example of ref, example of assign derefs. These are the same examples we had in class. And just reminders about how to get offsets, how to do the array stuff. It's just a pointer to handling variables. And that's it. So I gave an example here this is the example from class. So this is the full code example from class. The same directions for testing it with the wrapper. So just make sure you restrict yourself to pointer operations. Like this one is only pointer operations and assignment. So you can restrict yourself to that when testing. And that's pretty much it for CodeGen 4. Everything else is the same. There's a self-check here. Oh, I didn't update the self-check. Oh, I got to update that. But yeah, so everything's the same as CodeGen 3. Questions on CodeGen 4? Questions on pointer reference, pointer dereference, dereference assignment? All right, let's go through the entire example, which is a little intimidating. Okay, so I probably should have, oh yeah, actually I do have this here. So here's our, oh yeah, I guess we're just gonna do all of it. So yeah, let's just go through all the instructions. It'll do all the assignments, all the references. So my compiler, I put some little debugging output. So is this clear that this assign 8 to x is the same as this x to 8? That's pretty clear, right? All right, so let's assume the whole stack frame is set up. Let me reset this stack frame here to be at the point where we've called the function and set up the stack frame. And then let's go through each of these instructions and see how our state gets updated. And actually, I might as well put the registers here as well. Okay, so assignment from an immediate just works by loading the immediate value into RAX and then storing that RAX value into the address associated with X. Yeah?
You don't have to use RX, right?
You don't have to, yeah, you could do that. I did this because I wanted to be able to make this a template that was always the same for every variation. But yeah, you don't have to do that. All right, so after move 8 to RAX, how does the state of our machine change? So I've added registers to our state. This is our memory and our stack frame. This is registers. How does the state of our machine change?
So
Yeah.
first, REF holds the value 8.
All right, so that's
Also, the offset from REP, which is going to equal x, -24, that will also hold 8.
good. So the offset from RBP, 80 minus 24, which is here. This is 80 minus 24. 80 minus 24 is 56. It's address 56. So RBP minus 24 in our actual running machine, because I'm just assuming that we're at address 80 here, is address 56. Now gets assigned to whatever RAX is, which is 8. Questions on these two instructions? So immediate store of 8 to RAX, and then store of 8 to -24. Why is it -24?
That's the opposite.
That's the offset. So in our compiler, our local vars will associate each variable with an offset from RVP. That's how we store function local state. All right, good. So let's go to the next instruction.
It always goes by 8, right?
In our compiler, yeah, the data type for every variable, the width is 64 bits, so it's always 8 bytes, just to make things easier. It's pretty straightforward to use other bit widths, but it makes the compiler a lot more annoying to write. You have to save the data type, and it's a little more tricky to write. Okay, so this is the exact same code, except different values. So we move 9 now into RAX, and store RAX into now offset -32 from RBP, which is 48. So you notice how we're blowing away the register state, but our stack frame is keeping track for us all of the variables state. Okay, and now here's where we get our first pointer operation. We take the reference of x, so this is, remember, t1 equals $x. So this is the reference of x into t1. All right, so remember, in order to get, so references, we want to get the address of x. And so to do that, we generate code that will compute that address at runtime. Because remember, we don't know what the actual address is. We know what its offset is. And we know that RBP will hold the stack frame. So we can generate code that will compute this address for us. So the first instruction copies RBP into RAX. So now what's the value of RAX? 80. Good. Next instruction, we add -24 to RAX. So now what's the value of 80?
56.
56. Good. And then we store whatever RAX is into offset -40 from RBP. So offset -40 from RBP is address 40. That corresponds to variable TI. And now what's the value in this address? 56. So it stores whatever RAX is into this memory address. All right, good. So that's how the address of X got stored into T1's memory location. So now we have the deref of T. So this is T2 equals *1. So this is where we're dereferencing T1 and storing the value into T2. So deref T1 to T2. So first thing we do is take offset negative 40, which is the offset associated with T1. And we load its value into RAX. So what is the value in RAX now? Still 56. So the machine will actually do this copy for you, I think. It's not going to optimize it away for you. You could write another pass in the compiler to go over this code, because you can see here we have move RAX to negative 40, then negative 40 RAX. Optimizing compilers will actually notice this and remove it for you. But our compiler, making it easier to write, doesn't do any of this trickery. So this extra instruction, while seemingly meaningless, makes sense in the context of our compiler, because deref is a separate operation. So what we first do is we copy the value here into RAX, which just overwrites it with 56 again. All right, so here's one of our dereference operations. So how does the state of this machine change after this? Yeah?
It dereferences what's in RAX, so it'll get the value of 8 in there.
Okay, so why is it 8? Because 56, these parentheses say load from whatever address is stored in RAX. Address 56 is stored in RAX, so it loads whatever that value is into RBX. That value is 8, so now RBX holds 8. And then here we have a store from RBX into offset negative 48. So offset negative 48 from RBP is this address 32. So how does the state of this machine change after the highlighted? Yeah.
T2 equals 8.
Yeah, the memory address associated with T2, which is address 32, now holds 8. All right, good. Question so far? Yeah.
So basically, so basically, it kind of like changes the offset as the offset changes. So does the address and how do we get the address to the?
So remember this. Whenever you have a load or a store using this syntax, this is saying get whatever the value of RBP is, which is here 80, and subtract 48 from it. And that address computation happens inside the processor. And whatever the value of RBX is will be stored at that address. So here in the state of our machine, RBP is 80, and we're asking it to go to an offset of whatever RBP, so 80 minus 48, just 32, and store in that memory location. So it stores 8. Okay, so let's finish this up. So now we're at the assign deref, I call it. So we're doing star T1 equals 11. All right, how does the state of the machine change when we run this highlighted instruction? Yeah.
RAX is still equal 56.
Say again?
RAX is still equal 56.
Okay, RAX is still equal to 56, and that's because we asked the machine to go to the offset from RBP of negative 40, which is address 40, take whatever its value is, and store it into the register RAX. Yeah.
And then you put 11 into RBX.
Right, so our next instruction will store 11 into RBX. So it'll overwrite 8 and store 11. And then here we see another one of our pointer dereference operations. So, yeah.
Me?
Yeah, go ahead.
You take 11 and store it into the dereference RAX, which makes X, or store 11 into the memory address associated with X.
Good. So this will take RBX, which is now 11, and it will store it in the address given by RAX. RAX is 56. So the memory address 56 is here, and it'll store RBX, which is 11, here. Yeah.
So this is really close to kind of thing. So if we were to dereference RBX, what would happen?
If you dereference RBX,
Undefined behavior, or would it just what error would it get?
you wouldn't necessarily get an error. It would just load or store address 11.
Okay, so I just what?
Well, it's down here, right? It's down here in memory.
Okay. So would it not ground the year that starting
Well, I mean, these machines are byte addressable, so you can address individual bytes. I think, yeah. Yeah, so you can, so, you got to keep in mind that there's no distinction in the machine level between numbers, addresses, integers, strings. It's all just binary data. It's the operations that distinguish them. And yeah, when we program, we think in terms of these data types. But at the actual physical machine level, these are being mapped, encoded in numbers. Even the opcodes themselves, even this assembly code, is mapped into binary data. And you could dereference binary data. This is why you get seg faults and buffer overflow issues. You get seg faults because you're dereferencing stuff to an address that you don't have access to. The machine restricts your access to. But if you have access to it, you're going to get a silent failure and just your code's not going to work as you expect. But at the machine's point of view, it's doing exactly what you asked it to do. Okay, let's finish this out. So any other questions on the pointer operations? All right, so let's finish this out. Let's do x equals t3. I think that's what the next thing is, yeah. T1 equals x. All right, so what's the result in the machine after running this? Yeah, I think you got to run it first. Yeah. RAX is 11, good. So this is saying load from negative 24 offset from RBP. RBP is 80, minus 24 is 56. So it loads this value into RAX, finally overwriting it with something different. Okay, what about the next instruction? Yeah.
It loads the value of RAX, which is 11, into the memory associated with T3. So now negative 56 offset from RBP will now equal 11, correct?
Good, yeah. So RBP, again, we're storing RBP offset negative 56, which corresponds to T3 in our compiler. That's address 24. And we store whatever RAX has, which is 11 in this case. We store it there. All right, questions? Last minute questions. All right, so you have CodeGen 4. This is the end of the content for compilers. Next week we'll go over the final. And have a good weekend, everyone. Take care.